Well, hello, and welcome to another session on sequential circuits. Today's session will focus on timing. There are some general terms to review before analyzing the timing conditions that influence how sequential circuits are designed. First, the propagation delay is a type of delay that indicates how quickly the output of a digital circuit, or any circuit for that matter, responds to a change in the input. And the propagation delay is defined as the amount of time that it takes between the time the input travels half of its range to the time that the output travels half of its range. So the time between the 50% point on the input and the 50% point on the output is by definition the propagation delay, where 50% is defined as half the entire range of the input and half the entire range of the output. The rise time is specific to only one signal, any signal in a circuit or digital circuit. It's the time required for the output or that signal to increase from 10% of its total signal swing to 90% of its total swing. So if we look at this particular signal that's rising over time, the total signal swing, which we'll call delta, the 10% point is just the initial value, let's call it signal initial, plus 10% of that delta value, or the total range. That time associated with this value we can call T1. And in the rise time, the other time that we look at is the time required for the signal to reach 90% of its final value, or its initial value, plus 90% of delta, or the whole range. The time associated with that value is called T2, and then the rise time is just T2 minus T1, which is typically in nanoseconds or sub-nanoseconds for digital circuits. The fall time is very similar, and it's the time required for any signal in a circuit to go from its 90% point to its 10% point, where again the 90% point is 90% of the total range, or delta, and 10% is 10% of the total change in the signal, going from high to low this time instead of low to high. The setup time is a parameter that's specific to flip-flops in sequential circuits, and that setup time is the amount of time that the input to a D flip-flop, or any flip-flop for that matter, it's the amount of time that that input must be stable before an active clock edge. So if we look at an example of a D flip-flop, where the input is D and the output is Q, and in this case, shown here, the clock is leading edge triggered. The setup time is the amount of time that the signal D must be stable, or at a constant value, before the clock can go from low to high. That's the setup time. In a D flip-flop or any flip-flop that was trailing edge triggered, the setup time would be the amount of time before the trailing edge that the input must be stable, in order for the output to be stable as a result of a change in the flip-flop status. The hold time is a similar parameter, but it considers the time after an active edge of the clock. Again, in this example, this is a leading edge of the clock that's the active edge, and the hold time is the amount of time that the input, in this case we've used the example of a D flip-flop again, the hold time is the amount of time that D must be stable or constant before changing after the active or leading edge of the clock. In these three examples here, D in the first case is high for a long time after the leading edge, well past the hold time. So this is a good situation. In the second case, D is low for the entire hold time, another good situation. And in the third case here, D goes from high to low before the hold time has expired. So this is a bad situation. And bad means that we're vulnerable to generating an output that's unstable, metastable, or otherwise unknown. Yet another parameter that's specific to a flip-flop, again using the D flip-flop as an example, is the clock to output time. And the clock to output time is inherently a propagation delay. In this example here, we're using a leading edge, and it's the amount of time that once clock changes, in this case clock goes to high, how much time does it take for Q, the output Q, to react? And that amount of time, again defined as the 50% to 50% time as we talked about with the propagation delay definition, that amount of time is called the propagation delay of the flip-flop, or for short, TCQ, the amount of time for D to propagate to the output once the clock has changed. The logic delay, or logic time, is the amount of time that it takes for a signal in a sequential circuit to travel through the combinational logic between flip-flops. That logic time is either taken as the maximum or the minimum value, depending on what type of constraint we're trying to understand for the sequential circuit overall. And we'll look at two examples where we look at both minimum and maximum in subsequent slides. But the logic time loosely describes that time required for a signal to travel through any logic that takes place in between the sequential components, which in this slide are the D flip-flops once again. The maximum delay constraint is one of two primary constraints that we consider in designing sequential circuits. In a sequential circuit, if the clock period is less than this maximum delay, signals don't have a chance to propagate and become stable in the circuit before the clock triggers again. This leads to unknown or metastable outputs and general errors in our sequential circuit designs. So this maximum delay constraint ultimately restricts the maximum clock frequency as well as the minimum clock period of the sequential circuit. In other words, it restricts how fast we can go. The minimum period of the clock is given as the sum, worst case, or the largest values, of the propagation delay of a flip-flop plus the delay, the maximum delay that can be incurred in the logic in between flip-flops, and the setup time required to stabilize the input to a flip-flop before the clock can trigger. The minimum delay constraint, on the other hand, handles potential race conditions, where combinational logic can essentially move faster than a flip-flop can handle. This constraint typically happens after an active clock edge, either a leading or a trailing edge, and it constrains the hold time to be no larger than the sum of the propagation delay of a flip-flop and the minimum delay coming through the combinational logic. And we'll take a look at what that looks like in an example in subsequent slides. So keep in mind that there are two primary constraints we have to deal with after we've designed the basic logic for sequential circuits. The maximum delay constraint, which speaks to the maximum speed at which we can run the circuit, and the minimum delay constraint, which identifies how slow our flip-flops can be and still contribute to these circuits and these designs in a way that's functional and not subject to glitches. So let's start with an example of finding the maximum clock frequency. And what we're going to do here is go through every possible scenario in this circuit and find the worst case, or the slowest pathway for signals to travel. That slowest or worst case pathway will ultimately define the maximum clock frequency. So if we start here with flip-flop number 1, let's take a look at what's going on here. First, we have to acknowledge that this 1, which indicates a high signal, had to come from somewhere. So if we turn the power on, it has to stabilize for an amount equal to the setup time of the flip-flop. So as we boot the power or as we reset the entire circuit, we'll have to wait for that setup time in the worst case for this T input to this flip-flop to be stable enough to propagate into the rest of the circuit. That setup time is given in this example as 0.75 nanoseconds. And in this first flip-flop, it's the only component of the delay involved in the input to the flip-flop being converted to the output Q. If we take 1 over that 0.75 nanoseconds, we find out that the maximum clock speed, if flip-flop 1 were the limiting factor in this circuit, would be about 1333 megahertz. As you can imagine though, this first flip-flop is the quickest of the 4 flip-flops, so our clock speed is destined to decrease as we look at the remaining 4. In the next flip-flop, we have a few things going on. In order for the input to the flip-flop T in the second flip-flop to be ready to go, 2 things have to happen. First, there a propagation delay from the clock changing to the output of the first flip-flop has to happen, and that's the 0.9 nanoseconds shown right here. And second, there has to be enough time for Q0 to set up at T to make flip-flop 2 ready for a clock edge change. So first the signal has to propagate from the clock triggering to the output of the first flip-flop, and then it has to have enough time to set up at the input of flip-flop 2. That second parameter is the 0.75 nanoseconds shown in this equation for a total of 1.65 nanoseconds. If we take the reciprocal of that, we get a maximum clock speed of 606 megahertz. So between flip-flop 1 and flip-flop 2, we're now down to a maximum clock speed of 606 megahertz. Now let's take a look at flip-flop 3. In flip-flop 3, what do we have to wait for? Well, again, we have to wait for the propagation delay, or TCQ, through flip-flop 2, so that once the clock edge triggers, Q1 is ready to go. Then we have to wait for the logic delay associated with this NAND gate, T logic or T AND gate. And then again, we have to wait for the setup time with the input T to the third flip-flop. So that's shown here as first in flip-flop 2, we have to wait for the propagation delay. Then we have a logic delay through the AND gate of 1 nanosecond. And then we have a setup time at the flip-flop of 0.75 nanoseconds. The total is 2.6965 nanoseconds, and taking the reciprocal, we get a maximum clock speed of 377 megahertz. So given the choice between 1333 megahertz, 606 megahertz, and 377 megahertz, we have to take the worst case scenario, which is 377. But it gets a little bit worse than that if we look at the fourth flip-flop in this circuit. In this circuit, we now have to wait for a few things. We have to wait for the propagation delay, but which one? Well, ordinarily we would take the propagation delay through flip-flop 3, but if we look at the worst case scenario here, really the worst case pathway, or the slowest pathway to setting up the input to flip-flop 4, is here from flip-flop 2, where we have the propagation delay, or TCQ, through the flip-flop. Then we have a delay through one AND gate, a delay through another AND gate, and finally the setup time. So here's the delay for the 2 AND gates, and then finally we have the setup time for flip-flop number 4, bringing us to a total of 3.65 nanoseconds. And taking the reciprocal of that, we get 274 megahertz. So now evaluating all these worst case delays among the 4 possible flip-flops in our sequential design, we find that the limiting factor is here with flip-flop 4 and a clock frequency of 274 megahertz. So to guarantee the proper and consistent operation of this circuit, we'll have to run it no faster than 274 megahertz. On the other constraint, the minimum constraint, we're going to look at how slow our flip-flops can be before we can't operate them in our sequential circuit. And to do that, we're going to look at how fast it's possible for any one of the inputs to change to the flip-flop, and that will constrain the maximum hold time because the flip-flops can't be any slower than the minimum amount of time it takes for logic to propagate back to a change in the input. And here, since there's no logic between flip-flop number 1 and flip-flop number 2, the maximum time that it could take for this output, Q0, and input to the second flip-flop, the maximum amount of time it could take for the hold time on the flip-flop is constrained by this propagation delay. So it's possible that once the clock edge drops, there's a trailing edge, that a change in Q could happen within this 0.9 nanoseconds. And by then, this flip-flop has to be stable. We can't wait any longer than that. The hold time has to be stabilized before a new input appears at T. And that gives us a minimum constraint or a maximum hold time equal to that minimum propagation delay between the flip-flops of about 0.9 nanoseconds. Now in this circuit we have the same scenario. We're looking at the maximum hold time, which is the minimum constraint for sequential circuit design. And the maximum hold time in this case, since there's logic between each of the flip-flops, will be constrained both by a propagation delay from the flip-flop as well as a minimum, the fastest a signal can travel through the logic. Now let's look at the different scenarios for how a signal can travel through this logic. For example, if we have signal traveling through here, it goes through an inverter, an AND gate, an OR gate, and an inverter. That's quite a long delay. If we look over here at B travels through an AND gate, and an OR gate, and then an inverter. That's 3 gates. That's a little bit faster. But now if we look at the output here, after the output changes here, it's possible that it can race around, go through the OR gate and the inverter, and be here at the input to the flip-flop. And by that time, the hold time has to have expired on the flip-flop, meaning that the minimum constraint or the maximum hold time is equal to that minimum delay here. So the minimum delay, the race condition, is just a propagation delay of the flip-flop. Then out 2 can travel around through the OR gate and the inverter, and it can be at D in an amount of time equal to the propagation delay plus the logic delay caused by the OR gate and the inverter in series. So that constrains our maximum hold time. The difference between this example and the last example, of course, is that here we have a feedback loop, so we have to consider the propagation delay on this flip-flop as part of the minimum or the race condition for the sequential circuit. So in sequential circuits, we've learned that with combinational logic, there are propagation delays for every gate that must be considered in figuring out the maximum or slowest possible pathways for signals to travel, as well as the minimum or the fastest pathways. Flip-flops also have a propagation delay known as the clock to output time, and we have to consider both the setup time before an active edge of the clock and the hold time after the active edge when we design circuits so that there are no glitches, errors, or other metastable outputs that occur as a result of timing. Well, that's all today for sequential circuit timing. Thanks for joining us as we continue to explore the world of digital logic and circuits, and we hope you'll join us again soon.